going like this. This is the internal moment, which equals to Ks times theta 1 plus theta 1 plus, no, theta 1 minus theta 2. That is the internal moment acting on member AB. So the first moment equilibrium that we're going to get by taking the moment at B, the summation of moment, at B minus, and this will give us what? This will give us this result. You can take assume which one to be positive direction, assuming that we use clockwise as the positive direction. And this will give us this expression. That will become Ks times 2 theta 1 minus theta 2. That is just this from here. Minus P times L times theta 1. And this will be 0. And in the meantime, if we also look at the free body diagram at member BC, that means this is BC, another one is like this. This is B, this is C. And we use exactly the same way to look at the angles. First of all, this angle here is theta 2, and this angle here is theta 1 minus theta 2. So the actual amount of rotation at point C, we will determine that by what? By drawing a line along here. The actual amount of rotation is actually this. And this amount of rotation is 2 theta 2 minus theta 1. So by taking the moment equilibrium at point C, there's no substitute here, at point C, to be 0, and also by using counterclockwise as the positive direction. The moment equilibrium condition will give us this expression, which is Ks times 2 theta 2 minus theta 1 minus P times L times theta 2 will be 0. So remember, for member BC, we have two moments. One is acting on the right, the other is acting on the left. Now, if we look at these two, these two expressions, and we can put them actually in a matrix form. So if one is member AB and this is actually member BC, is for this one. We can actually express these two equations in the matrix form by isolating variables theta 1 and theta 2 and into a vector form. So the equation 1 and equation 2, we're going to do this. Equation 1 actually equals to, if you just put everything about the theta 1 together, and this will actually become 2 Ks minus PL, the whole thing times theta 1, minus Ks times theta 2. to be 0. Right? Right? We just rearrange everything. Why we are doing this? Because we want to separate theta 1 and theta 2 from this expression. And similarly, for equation 2, you will move everything related to theta 1 to the first term and put everything else related to theta 2 in the second term. So the first term will just simply becomes negative ks times theta 1. So you can consider this is the coefficient with theta 1. What about for theta 2? You put whatever is left together, and that becomes plus 2ks minus PL times theta 2. This will be 0. Correct? So here we did nothing but just rearrange these terms. So we can separate theta 1 and theta 2 from these two polynomials. That's the whole idea. Once we have arrived this expression, then we can write the following. And then the expression can be written like this. We'll write this like a matrix. The coefficients associated with the first theta 1, which is this one here. This is going to be element 1, 1, and the negative ks will be the element 1, 2. Negative ks minus ks is going to be element 2, 1, and the 2ks minus PL will be element 2, 2. So the whole thing can be written like this. That will be 2 ks minus PL or negative PL minus PL ks, I'm sorry, minus ks, and 2ks minus PL. The whole thing times a vector, which is theta 1 and theta 2. This equals to a 0 vector, 0 here and 0 here. This is the matrix form for equations 1 and 2, right? Okay. Now, the next one is what? Step 4. Now in step 4, for every combination of theta 1 and theta 2 not to be 0. Actually, it will be 0 vector. So it should be 0 vector like this. That means non-trivial solution. Because when theta 1 and theta 2 are zeros, and there's no buckling, there's no deflection. So we have to make sure that there's no non-zero solutions here. The determinant denoted by det of this matrix, which is 2ks minus PL and minus ks and 2ks minus PL. The determinant of this matrix must be 0. So what we need to do is just to calculate the determinant of this matrix. So how do we calculate the determinant of this matrix? For 2x2, it's extremely easy. If you remember this from, I don't know where you learned. Linear algebra. Suppose you have a matrix and it has 4 elements, A, B, C, D. The determinant of this matrix to be 0, that simply means A times D minus B times C must be 0. That's how you calculate the determinant of a 2x2 matrix. So with that, we know that the condition we can apply is just 2ks minus PL minus this square minus ks squared to be 0. Right? It's just going to be like this. And then what we're going to do is just to expand this. So the following, of course, you know how to do it, but I will just write the math so you can also practice this. Of course, this square term will be expanded to be 4ks squared minus 4ks PL plus PL, the whole thing squared, minus ks squared to be 0. Right? And of course, that will become 3ks squared minus 4ks times PL plus P times L squared, the whole thing. And you can certainly, by observing the factors, or you can use other approaches. And this is a simple problem because we can see that this can be expressed by this. Can be written as the product of these two terms. The first one, the 3ks minus PL times ks minus PL. This will be 0. So what does that mean? That means in order to make this to be true, any one of them can be true. You just need one of the conditions. That means either 3ks minus PL must be 0 or ks minus PL is 0, correct? That can hold this condition be true. So this is our governing equation. And then we have two roots. And from the first one, we can determine that the critical load P equals to what? 3ks over L. That's from the first one. And from the second one, P will just be ks over L. Right? Now tell me which one is our solution. If it's not clear, you can use the force deflection figure that we've been used before. And this is what we use. Try to picture this. You have delta, you have theta, and you have P. Now we have found two different values. One of them is ks over L. The other is 3 times of this value, right? That means what? That means we have one value here, and that is, you may call it ks over L. The other is 3 times, right? So 3 times